Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Right, so welcome back. Our next talk is going to be by Raoul Savani from the University of Liverpool. We'll be talking about learning Nash Equilibria of games using payoff queries. Over to you.
Thanks a lot. Thanks to the organisers for the invitation. Pleasure to be here. So this is joint work with John Fernley, Paul Goldberg and Martin Gehring. So it's about applying ideas of query complexity to game theory, and in particular finding Nash equilibria. So the motivation, some rough motivation. So games of practical relevance might be very large, and obtaining or maintaining a full representation of the game may be costly. So the basic challenge here is to find equilibria with only partial knowledge of the payoffs. So as an example, consider a routing game where you know the network, but you don't actually know the latency functions on links in the network. Okay, so some related work. So actually what inspired us to do this work was a talk by Mike Wellman. He came to Liverpool and talked about empirical game theoretic analysis, where he basically had a simulator for limit order book markets and another simulator for ad auctions, and essentially he wanted to study what good strategies would be in these particular domains, and he did so by actually using the simulator to generate payoffs and then solve the resulting games. And so he basically asked the question, is there a theory of how many of these type payoff queries we need to be able to find equilibria? There's also a history of studying best response dynamics, for example, in potential games, which can actually be thought of in this query setting, since what you're actually doing is, for a particular strategy profile, you're asking what payoffs are and what payoffs would be if you switch to some related strategy profile, and then actually switching if it's profitable. There, the dynamics are intended to capture decentralized behavior, say. For example, individual players locally improving. It's not completely decentralized in the sense that you normally assume synchroneity. So one player updates, everyone knows what that player does, and so on. But it's meant to capture these decentralized settings. That's quite different from what we're going to do. We assume that we have a centralized algorithm that chooses queries and tries to find equilibria with few queries. Okay, so I think we can place the work within general framework of looking at constrained algorithms for finding equilibria. So some very natural constraints that people have looked at in equilibrium computation, uncoupled algorithms, which means that essentially a player is only using her own payoffs to make decisions without knowledge of other players' payoffs. Communication constrained algorithms, where actually players start knowing their own payoffs but not the payoffs of others, and there is a cost associated with communicating payoffs. And oblivious algorithms, which actually only query the game for very specific types of questions like, is this particular mixed strategy profile an epsilon equilibrium, for example? Okay, probably the restriction we know best is a restriction to polynomial time algorithms, where when we're asking, can we find an epsilon Nash equilibrium, what's the best epsilon Nash equilibrium we can find? We mean, what's the best epsilon Nash equilibrium we can find in polynomial time? And in general, studying these types of constraints, when we can actually prove lower bounds or impossibility results, they inform us about what a successful algorithm needs to actually do. Okay then, so what do I mean by payoff query complexity? I mean that we have some class of games G. So in this talk, we're going to consider congestion games and strategic form games. And we have a particular solution concept in mind. We're going to consider both exact Nash equilibria and approximate Nash equilibria. And then we say that the query complexity is the smallest n, such that there's an algorithm A that, given n payoff queries to a game, can find a solution to G. What I mean by a payoff query is you tell the querier specifies a strategy profile and finds out the player's payoffs for that particular strategy profile. Okay then, so note that this imposes no computational bound on the algorithm. In principle, we could have a polynomial query complexity, but actually you need to use exponential time given those queries to actually find the equilibrium. And also note, naturally, but it's worth stating explicitly, that queries can depend on the responses to previous queries. So you do a query, you get the answer, and then you choose your next query. Okay then, so specifically for strategic form games, initially the querier is only going to know the number of players, and let's assume that all players have the same number of strategies, the number of pure strategies of each player. So we're going to select a pure strategy profile, we get the corresponding payoffs back. Now they're k to the n pure strategy profiles, and of course we could learn the whole game by using that many queries. But that's not very interesting. What we want is we want algorithms that require only a small fraction of this many queries. And what this means is, as we'll see for, say, a Bimatrix game, sometimes we have to settle for approximate equilibria. Because, as we'll see, as one of the first simple results, if we want an exact equilibrium, we need to find out all the payoffs. Okay, so rough outline of the talk. We'll talk a bit about Bimatrix games, a bit about congestion games on parallel links, and then I'll tell you a bit about what's in the paper without going into detail in case you're interested, and then we'll discuss some future directions. Okay then, so just to make sure we're clear on what queries look like and what the idea is, let's consider pure equilibrium Bimatrix games. So for simplicity, since it means I just need to draw a single payoff in each box, we're just going to look at zero-sum games. And in fact, for our lower bound on exact equilibria, zero-sum games already can have that lower bound. Okay, so if I just query a particular cell, I just get back a payoff. Okay, so this is a zero-sum game, so this means player 1 would get -1. Player 2, the minimizer would get 1. What I've given what I've given as a query is I've said, give me the payoff for row 3, column 1. I can't do much with that, so if I really want to try and find a pure equilibrium, I at least need to find out if a particular cell is a best response. So let's actually query the whole first column. What would I do next? I note that in this column, the first row is a best response. So if I'm going to find a Nash equilibrium that uses this particular column, I'm going to have to now query the first row. But unlucky, that's not actually a pure Nash equilibrium because the column player is now, actually, I forgot to change the payoffs. That actually is a pure Nash equilibrium. The column player is minimizing, but of course, Bimatrix game, zero-sum or not, may not actually have a pure Nash equilibrium. So we're going to go on and look at mixed equilibria. Okay. So any questions before we go on the model? Okay, so mixed equilibria. Again, zero-sum setting. I've just highlighted the diagonal because in this particular game, we've got ones on the diagonal, -1s everywhere else. This is meant to indicate a hide-and-seek game where one player is simply trying to pick the same cell as the other, find the person, and the other player simply wants to be elsewhere. So the point here is there's a unique, uniform, completely mixed Nash equilibrium. Okay, so player 1 mixes uniformly over the rows, player 2 mixes uniformly over the columns. It's not a fair game because, so it depends on the size of the game exactly what the value is. But the point is that there's this unique completely mixed Nash equilibrium, and if we tweak any payoff in the game, we're actually going to change the probabilities. That's the crucial thing for the simple lower bound. And what that actually means is this is a zero-sum game. We can also tweak the probabilities tweak the payoffs in such a way to preserve the zero-sum property, and that will also tweak the unique equilibrium probabilities. So, first simple observation is the payoff query complexity of finding an exact equilibrium is k squared for a k by k game, even for zero-sum games. Okay, so what we're going to do is we are going to relax our notion of equilibrium. We're going to allow approximate equilibria. Yeah?
Do you know what happens if you constrain the possible payoffs, say only 0 and 1, or if you look at symmetric games?
No, I have not thought about that at all, actually. But it's a good question. So if we so we're going to look at approximate equilibria now, and for doing that we need to restrict the range of payoffs in order that our measure epsilon of the approximation quality actually makes sense and is consistent across different games. Okay, so we're going to assume all payoffs are in the range 0, 1. And in a Nash equilibrium, players cannot gain by unilateral deviation. Okay, they cannot gain anything. In an epsilon Nash equilibrium, where for these type of games where the payoffs are between 0 and 1, epsilon is also between 0 and 1, a player can gain at most epsilon by unilateral deviation. Okay, so you have a pair of mixed strategies. Against the mixed strategy of your opponent, you get a certain expected payoff for your mixed strategy, and you now look at what you would get by playing pure strategies against that mixed strategy, and you want to ensure that you can gain no more than epsilon by switching from your mixed strategy to a pure strategy. Okay, so for epsilon equals 0, we've seen that the query complexity is k squared, meaning you have to find out every payoff. And we're going to consider 3 intervals for larger epsilon. Okay, so first, at the far right end, if epsilon's 1, then it doesn't matter what we play. But actually, even if epsilon is just bigger than 1 minus 1 over k, we're in good shape. We don't need to make a single query because we can just play uniformly over all of our strategies. So then, okay, so we've kind of dealt with really bad approximations. Some might claim even 0.3 or something is really bad, but actually that's, the best we can do in polynomial time for a Bimatrix game is 0.33. So that gives you some idea of where the state of the art is. No, actually, sorry, I mean the best we know for getting payoff query complexity, if you know the whole game, the best epsilon we can do in polynomial time is about 0.33. So just to give you some idea of where we're at in terms of the state of the art for standard algorithms for finding approximate equilibria.
It's a totally different question. You want to see what is the number of queries.
Absolutely, yes. But of course, we need to, we might use related technologies because in the end we need to find an equilibrium. So for example, for congestion games, what we do is we take an idea for an existing algorithm and we do a payoff query efficient implementation of that algorithm. So they are different, but I would claim there's a relationship. In fact, one of the reviewers of the EC paper actually said, "Why should this even be different from normal computational complexity?" And I guess, it clearly is because if we look for an exact we can find an exact equilibrium of a zero-sum game in polynomial time, but we need to know the whole thing for that. So there is a difference. You're right, but I was just commenting that that actually. The state of the art for finding approximate equilibria is not that great, irrespective of payoff query complexity. Okay then, So then, okay, so now we're going to look at the range between a half and 1 minus 1 over k. And I'm going to show you, again, it's simple, that the payoff query complexity is between k and 2k minus 1. For the upper bound, we're going to simulate an algorithm of Daskalakis, Mehta, and Papadimitriou that obtains a half Nash equilibrium. And we actually just directly implement their algorithm. So if you know it, there's nothing new going on here. So their algorithm's very, very simple. You simply pick an arbitrary pure strategy. So let's pick the first row. And you now find a best response to that. You now take that best response and you find a best response to that. Okay, so what we've done is we've found the best response against the first row of player 2, who in the zero-sum game is minimizing. So we get this -1, and I've kind of broken my promise that the payoffs range between 0 and 1, but it's not important for how the algorithm's implemented. And now we're going to find a best response against that. And now simply the players are going to play uniformly on these 3 strategies that we've identified. The row player is going to mix between the original arbitrary choice of his pure strategy and the best response to the best response to that pure strategy. And the column player is going to play the pure strategy that's a best response to the original arbitrary choice. And the reason this is at least a half Nash equilibrium is because essentially each player is putting half their probability mass on something that's, the column player is putting his probability mass on something that's a best response to something played half the time, and the row player is playing a best response with probability a half. Okay, and what did we need? Well, we just needed 2k minus 1 queries. And now for the lower bound, the adversary against the querier is going to report a game of the following form. It's going to have zeros everywhere, but somewhere in there's going to be this row of all ones that the adversary has in mind. But of course, that row of all ones, he's going to report it as the very last row that gets discovered. And the querier has to discover that row because there has to be probability mass on that row in order to ensure that epsilon's less than 1 minus 1 over k. Okay, where of course, so k is the number of rows. Okay, any questions? Right. So now now we're doing between 0 and a half, strictly less than a half. So it's easy to find a half, both in terms of computational complexity and in terms of payoff queries. Now we're in the bottom part, 0 to a half. We know at 0 we need k squared, and unfortunately we don't have a good upper bound here. So what I'm going to present to you is a lower bound that basically says that there is an epsilon strictly greater than 0, so that we actually need superlinear number of payoff queries. So this is in contrast to needing between k and 2k minus 1 for a half and above. We're going to need a superlinear number for some epsilon strictly greater than 0. I'm going to just sketch. I'm going to do a fair bit of hand waving now, so excuse me, but it's slightly technical, but the idea should be clear enough. And so essentially, as epsilon goes to 0, epsilon actually features in the payoff query complexity bound that we get, but essentially as epsilon goes to 0, we get k log k. Okay, so we're going to start with a non-square game, which later we can make square by duplicating rows and columns. And it's actually going to start off as a zero-sum game. And it's going to have, it's going to be L columns, and L choose L over 2 rows for some even L. and we're simply going to have row payoffs with half of the entries being 1, the other half being 0, and we're going to have all the different rows of that form. Okay, so the first thing to note is the game has value a half, and it's again a game where people mix uniformly. And now consider an epsilon equilibrium where epsilon is actually less than a half. So no player can receive too much probability. So the basic story here is if any column receives too much probability, then the row player can fix on those rows that happen to have 1s in it for that column and actually get a better payoff. Okay. Also, the row player's payoff cannot be too high because it's a zero-sum game and the game has value a half. Okay, so we need to have the column player getting a suitably high payoff as well relative to his best response. Okay, so now suppose that a query algorithm makes very few queries and achieves this epsilon less than a half. I'm going to argue for a contradiction with just hand waving though. So then there must be a row that also received very few queries. Okay, there are very few queries overall. In particular, there's a row that received suitably few queries. Not saying what suitably is. And actually, because the column player doesn't put too much probability mass on any column, actually there's not too much probability mass on queried cells of R. Okay? So there is suitable amount of probability on cells within this row that we have not queried yet, and we're free to set them as something different, which is what we're going to do now. So we're going to replace all the unqueried cells in that particular row with 1s. What this does is it means that now row R will have a high payoff. And this is going to be a pure strategy, best response, that's going to break the equilibrium, the epsilon equilibrium property for the row player. Okay. Was that believable? Okay, and then that's not actually a square game, but then we can duplicate rows and columns to actually make it a square game. And so we actually get I see, it looked really messy. I considered showing some of the expressions, but I didn't in the end. We actually get an expression that depends on epsilon as well. And for epsilon less than an eighth, this thing works. So there's an epsilon, so for epsilon less than an eighth, basically, we have something that's superlinear. But it's very interesting what we can do, what decent upper bounds are between 0 and a half. We leave that completely open. Okay then, any questions at this stage?
So intuitively is the fact that we don't know any good polynomial time algorithms a barrier that prevents you from coming up with query efficient algorithms? Just intuitively.
I'm not so sure. I would say more the barrier is you solve, typically for those algorithms, you solve an optimization problem where you actually need an exact solution, or we don't have techniques to actually reason about getting approximate solutions to that. And so, we simply would need new machinery to be able to somehow argue about applying any of those techniques to get you less than something for a half, basically.
So you don't have any candidates?
No, not even a candidate, yeah. I wouldn't, it might be doable, but I wouldn't cherish taking some of those LP-type algorithms that get you even worse than 0.33, worse than the very best. I wouldn't cherish the idea of making a query-efficient implementation, if it's at all possible. But still, I think the general question is interesting. Sorry? Yeah. Okay, so I started at 3:30, did I? Okay. So we're going to talk about congestion games now and parallel links. Okay, so this is essentially as simple a congestion game as you can imagine. We do have some results on more complicated congestion games in the paper, but this is, I think, a nice one to present. So for a general congestion game, we're assuming that the querier knows the graph, knows the number of players, but knows nothing about the latency functions. So what's the query complexity of finding a pure equilibrium? Okay? We didn't consider approximate at all. We just proved results on finding an exact pure equilibrium, which exist in these games by a potential function argument. And actually, they can be computed in these games. In the computational complexity is polynomial. Okay then, so we're going to look at two link examples, and so I'm going to represent the to start with for a lower bound. And so the idea is we're going to represent strategy profiles as just points on this x-axis, which say how many players on a red link, and we've got a blue link that has all the remaining players on it. We just have two links in this example. Okay, and so these red lines are just meant to indicate if I stick one player on the red link, then the latency is 1, which we read off the y-axis, and that's true all the way up to having 4 players on the red link. But as soon as I have 5 players on the red link, the latency goes up to 3. Okay, and then so the point about the latency function is it's non-decreasing. And we have a similar latency function for the blue player. And then a Nash equilibrium is a strategy profile where neither player can gain, so no player can gain by switching from their link. So no one can switch from the red link to the blue link and gain, or vice versa. And we have an equilibrium there, essentially where the costs are equalized. They're not exactly equalized here, but near where the latencies are equalized. Okay, so the first thing I'm going to show you is a simple log n lower bound, which uses only 2 links. Okay, so I'm going to actually tell you up front that the blue link has always latency 1. And then I'm going to simply I'm going to maintain 2 variables, lower and upper, L and U. L is going to be at 0 to start with, U is going to be at n, which is 10 in this example. And I'm simply going to do the natural thing. If you report me something less than halfway along, I'm going to make all of those costs 0. If you report me something now past halfway or at the halfway mark, I'm going to report all of those as having cost 2, and you need to find the switch point. Okay, so essentially you can solve this problem by binary search, and you can do no better than that. Okay then, so given that if we can only query strategy profiles, we also have a plus m in our lower bound that comes from a separate type of instance. So the log n came from a very simple instance where we had just 2 links, n players. But now imagine another extremely simple instance with 1 player and m links. If we can only query strategy profiles, then we need to query all m links. So that gives us a plus m. For the upper bound, I'm going to get rid of this plus m consideration, and I'm going to look at a slightly stronger query model that removes some of the details. But I still believe it's interesting because the log n lower bound still applies. Because note, because the blue costs are always constant here, it doesn't help you at all if you can actually query some other stuff on the other link as well or whatever. So so I probably wasn't clear there. To be absolutely clear, we're going to now allow queries where there is at most n players on each link. More generally in a congestion game, at most n players on each pure strategy. Okay, we never need more than n players on a pure strategy because we never need at most n. But of course, we potentially gain something by allowing, if you've only got 10 players in the game, allowing 10 to go on 2 different paths actually might buy you something. We believe that we can implement our upper bound using the more restricted queries, but it would be a big mess and we didn't bother. Okay, so we've allowed these slightly stronger queries, and then the lower bound is just a log n without the plus m, because of course if you're allowed to query up to n on each link, a one-player game, m links, I do one query, I find out the best link. Okay then, so the upper bound we're aiming for is this thing, and I'm going to do it by talking through an algorithm, more hand waving. The algorithm is going to work by finding equilibria for blocks of players. So we're going to start with a big block of players, conveniently chosen here to be a power of 4. If the thing is not a power of the amount you're going to divide your block size by each time, then you actually need to maintain a special link and prove some extra stuff along the way, and I'm not going to go into the details of that. So here, this k equals 4 in the title, that's the amount we're dividing the block size by each time. So we have 64 players, 3 links, and we're dividing the block size by 4 each time. Step 1 is to stick all the players on the cheapest link. And we can do that with a single query with our stronger query model. Now we're going to do, and now what we're going to do is we're going to have an outer for loop that just brings this block size down by factor k each time. And we're going to always maintain an equilibrium of, well, what you'd imagine an equilibrium to be. Only blocks can deviate. They have to stay together as a block. Okay? So we start with an equilibrium where the block size is all the players. We find the cheapest link. That's an equilibrium. We're now going to divide that block size by 4. Those are blocks, and the blocks can deviate, and we want to find an equilibrium with that smaller block size. So what we're going to do is we're going to query up, by which I mean we're going to look at places that blocks can move to. And so we're going to check what would happen if we put blocks on places, increasing the amount. And then we're going to make a guess. Okay, not guess, we're actually going to do a binary search. How many players move, how many blocks move, and using another binary search, we're going to determine if that candidate number of blocks to move is actually correct. So we have an outer loop that basically reduces the block size each time, and then we do a double binary search. And I'm going to try and indicate that with a couple of diagrams. Okay, so we're going to set the new block size to n over k. So now we've got groups of 16 players that are going to move. We've already got 64 players on link 3, and the latencies are shown. And I'm not drawing any red on link 3 because at the beginning we're only going to move away. We're not going to move anyone to link 3. And so what we're going to do is we're going to look what happens when I put 16, 32, 48 players on the other links. And that's what's indicated by the 3 red blocks on each of those links. So we see that somewhere between 20 and 40 is the latency if we stick 16 players on link 1, and then what happens if we stick another 16 on, and so on. Okay? Then what we're going to do, okay, so the thing to notice is, apart from some special cases that we won't concern ourselves with here, is in general, only k-1 players should be going to another link. K-1 blocks should be going to another link. If more were going, k is the amount we divide by. If more were going, then that should have been an equilibrium in the last stage. Okay? So that's one crucial aspect. We can bound the number of groups that move as essentially km. Okay, so what we're going to do is we're going to, once we know these, we do this once for finding this new equilibrium for the reduced block size, and then we do a binary search on the number of blocks that move. So what we're going to do is we've done this querying up, and we get literally a list of costs associated with all of these red lines, and we just order that. It's a multi-set of costs, and we just order it from small to large. We're going to guess the number of blocks that move, and we're going to pick out the k+1 smallest entry from this ordered list. So if that number move, we need to ensure that on every link we have no more than the q+1 cost for that link. And so what we're going to do is we then do another binary search to determine how many would need to move to ensure that we have cost no more than the q plus 1th element. And then we simply check, is that the right number? When we add up all the number that need of blocks that need to move, is that actually the original q that determined the q plus 1th smallest entry? Okay, so to give an example, an easy example, because we only have people on one link to start with. In general, you'd have people on lots of links. But to give the basic idea, what we've done is we did the querying up. We got these numbers here. We've also queried up from the yellow link, but I actually made the yellow link in this example. I made its latency constant for higher numbers. So that's why you see a string of 90s in there, which is at that level. So we've ordered these costs. So actually this one was 31, the cheapest one to have 16 on it. We've ordered them. We've guessed a candidate. 3 here is the number of blocks we're going to check if they move. We've picked out the 4th entry from that ordered list. And now that guess was correct if, so because we want to move 3, we need to check if 3 is the smallest number of blocks that we need to move from link 3 in order to satisfy that link 3 has a suitable latency remaining on it when we've moved those blocks but left some on there potentially. And so that's true if when we take away 3 blocks, the cost is less than or equal to 63. But if we only remove 2 blocks, actually the cost is then greater than 63. If that's true, then actually what we do is we just stick, then 3 is the right number to move, and then we literally stick, the button's on the side somewhere, is it? Oh, there. So we'd literally stick the cheapest, second cheapest, third cheapest, we would move the blocks to those 3, and then we would have an equilibrium for the reduced block size. Okay then, so very roughly, for each block size, we do a binary search on Q, and for each Q in this binary search, we do essentially K payoff queries to determine C min Q, log KM payoff queries to determine the QIs in parallel, which is the number of blocks we need to shift from each link. And so for any particular Q, we're doing this K plus log KM. The binary search on Q itself adds an extra log KM factor. So basically, this is how many we do for each block size. And then, of course, we need to account for the outer for loop, where we start with n players and are dividing by k each time. So that's log n over log k. And so if we just picked 2 for k or 4 for k, we would get log n log squared m. And the whole thing would look more pleasant. But actually, we improve slightly by picking k as log m. And we get this extra log m in the denominator. Okay, so it sounds fancy, but this is essentially a polylogarithmic factor away from our lower bound. But actually, with this being only log n, maybe actually one can do much better than this. It's completely unclear. But the important point to note about lower bounds here is our lower bound literally uses 2 links, n players. It doesn't feature m at all. We spent a bit of time thinking, but we failed to come up with a lower bound that was actually of the form f of n, g of m, where they're both non-trivial. So actually getting this kind of simultaneous dependence on n and m from a single example. And that's one of I'd say the key open problems there. So I've run out of time. I'll just briefly say what we do for DAGS, more general things, is we actually discover equivalent cost functions. So imagine a path. I can't find out exactly the costs of the individual edges because I only ever find out the cost of the whole path. But what we do is we find out equivalent cost functions that allow you to then solve the game using a normal algorithm. That's not ideal. One would actually like to discover less, to do less payoff queries and still be able to do it. But actually even doing this is quite involved because you need a scheme to actually infer things about edges from paths. For graphical games, we also do essentially a discovery of the whole graph structure. There we assume you don't know the graph structure and the payoff functions. But again, that's not very attractive because you've discovered everything. And what we're really interested in is examples like for congestion games on parallel links, where one can actually discover not too much about the actual payoffs and still find an equilibrium. Okay then, so some open questions to wrap up. What about an upper bound for epsilon less than a half? Lower bounds for congestion games that actually feature M in it in a non-trivial way. Other types of games, 3 or more player strategic form games, asymmetric network congestion games. I think probably we've actually finished that case, but it's very messy. Just discovering all the payoffs there, you need slightly stronger queries, and it turns into quite a mess. That actually relates to some work of Alon et al., where they're essentially trying to do economical graph discovery in a rather similar model, but they have a bit of a cheat in their paper. They allow you to reuse edges multiple times, which gives you a lot of power. And we don't. So in some sense, this work, even though it's maybe not that appealing in terms of getting great upper bounds for payoff query complexity, it actually has applications in other models that are being considered for just graph discovery. And finally, what about other query models? In particular, if we're really claiming this is of any practical relevance at all, maybe we should consider noisy payoff queries where we don't necessarily get back actually an exact payoff. We might maybe get a noisy payoff, or perhaps even best response queries where we get back just a best response. Things like fictitious play can be seen as getting back best responses to mixed strategies. Or maybe even we actually just get back yes or no answers to questions of the form, is this epsilon best response or something? Okay then, thank you very much.